Now today we are beginning the chapter number 6, that is electromagnetic induction. First we shall discuss the experiments of Faraday and Henry. Now here comes the first experiment. Here one coil is shown, C1, and it is joined with the galvanometer. Okay. Now deflection of galvanometer, what does it show? It shows the presence of electric current in the coil. Okay. So the deflection of the galvanometer shows the presence of the electric current which is passing through the coil. Now the bar magnet is taken towards the coil. Okay, it has some speed and it is moving towards the coil. The deflection is seen as long as the bar magnet is in motion. If you keep the bar magnet here close and stationary, okay, then the deflection will become zero. So as soon as it stops, deflection becomes zero. The galvanometer does not show any deflection when the magnet is held stationary. When the magnet is pulled away, if it is taken in this opposite direction, then the direction of the galvanometer's deflection will be opposite. So the current produced will be in the opposite direction. Say for example you have galvanometer and it is having 0 here. Okay. Now when you are taking the magnet towards the coil, then the deflection is say towards right. Then when the galvanometer is taken away from the coil, then its deflection will be towards left. Okay. So if the direction of motion of the magnet is opposite to earlier, then the deflection will be in the opposite direction. Okay. Moreover, when the south pole of the bar magnet is moved towards or away from the coil, the deflection in the galvanometer are opposite to observed with the north pole for the similar movement. If you are taking the north pole towards the coil and the deflection is towards right, then if the south pole is taken towards the coil, then the deflection will be towards left. Okay. Further, the deflection and hence the current is found to be larger when the magnet is pushed forward or pulled away from the coil faster. If the speed of movement is faster, more current is produced. Now if the bar magnet is held fixed and the coil C1 is moved, say for example you keep the bar magnet stationary, okay, keeping the bar magnet stationary, say bar magnet is kept here, and the coil which you are having, which is containing the galvanometer with it, okay, so by keeping the bar magnet stationary, if you move the coil towards the magnet or you take the coil away from the magnet, the galvanometer shows the deflection. Okay, so there must be a relative motion between the bar magnet and the coil. Okay. Motion between the magnet and the coil is now responsible for generation of electric current that can be understood from this particular experiment. Okay, so now if the bar magnet is held fixed and the coil C1 is moved towards or away from the magnet, the same effects are observed, that is deflection in the galvanometer is seen. It shows that there must be a relative motion between the magnet and the coil. Okay, there must be a relative motion between the magnet and the coil. Okay, which is responsible for the generation of electric current, which is known as induction. Okay. Now there is another experiment. Here one figure is given. Figure shows the bar magnet is replaced by second coil C2. So another coil is kept here. Okay, that is a C2 coil. Okay, instead of bar magnet we are having another coil, and first coil is having galvanometer. So there is no source of electric current. Here there is a battery, okay, which is a source of electric current. So when the circuit is completed, the current will pass through the coil C2. Okay. Now C2 is connected to a battery. A steady current is passing through C2 which produces the steady magnetic field. Okay. Now as you know, when the current is passed through the coil or any say conductor, then the magnetic field is produced around it. Okay. As coil C2 is moved towards the coil C1, now what you are doing, you are taking the coil C2 in the direction towards C1. So you can see that magnetic field lines which were associated with this second coil will now associate, or the number of field lines associated with this first coil will increase. Okay. And because of this, when you are taking this another coil C2 in the direction of C1, here galvanometer shows the deflection. Okay. When C2 is moved away, the galvanometer shows the deflection again, but this deflection will be in the opposite direction. Okay. The deflection lasts only until the coil C2 is in motion. Okay. So this is what about second experiment. Okay. When the coil C2 is held fixed, C1 is moved, the same effects are observed. Now you keep the coil C2 stationary. Okay. Don't move this coil. Now you are moving this coil either towards the second coil or you are taking away from the second coil. When you are taking it towards the second coil, then say for example galvanometer shows the deflection towards right, and when you are taking it away from the second coil, then it will show the deflection towards left, that is opposite to the earlier deflection. Okay. So these are the observations which are obtained from this experiment. Again, it is the relative motion between the coils that induces the electric current. So there must be a relative motion. One should move with respect to other. Okay. Try to understand this also. If both are taken together with the same speed, both are taken together with same speed, okay, either towards right or towards left, what will happen? Just think. Okay. Now we move further. Okay, experiment number 3. The above two experiments involved relative motion between the magnet and the coil and between the two coils respectively. Okay. So there must be a relative motion. Through another experiment, Faraday showed that this relative motion is not an absolute requirement. Now see, figure shows two coils C1 and C2. Okay, held stationary. Coil C1 is connected to galvanometer. Now see this particular experiment. Okay, what is done here? Here this coil C1 is connected with galvanometer, which shows the presence of electric current, and here this second coil, okay, that is connected with the battery and a key. There is no connection between these two now. Okay, rather there were no connections earlier also, but now the key is tapped. Once the key is closed, then it has been open. Close, open means current is switched on and off with the help of this key in this coil C2. When you are switching the key on and off, a momentary deflection is seen in this galvanometer which is joined with this first coil. Okay, so you are at the time of switching on and switching off, a momentary deflection is seen in the galvanometer. Okay. It is observed that the galvanometer shows a momentary deflection when the tapping key K, here which I have shown, this is a tapping key K, you can switch on and off, is pressed. The pointer in the galvanometer returns to 0 immediately. For a moment you see this deflection. Okay, if the key is held pressed continuously, if you are passing the current through this second coil, you keep on pressing, just keep the key pressed, then what will happen? Okay, if the key is held pressed continuously, there is no deflection in this galvanometer of the first coil. Momentary deflection is only seen when it is switched on, just a deflection, and then again it comes back to zero. When the key is released, momentary deflection is observed again, but in the opposite direction. Okay, it is also observed that the deflection increases dramatically when the iron rod is inserted into the coils along their axis. If you put the iron rod within the coil, okay, then this deflection dramatically, or it increases rapidly. Okay, so these are the observations. Okay, now during this whole process, let me try to explain that when you are momentarily pressing this key, what happens? Or rather, you keep the key pressed, but when you press, what happens? Initially, when there was no current, no magnetic field was zero, so no magnetic field lines were associated with this second coil as well as this first coil. But when you press it, then the field lines associated with both the coils changes, and then the field lines become constant. There is no change in magnetic field lines when you keep the key pressed. Okay, so when there is a change in magnetic field lines, from 0 to some maximum value, then it remains as it is. Okay, from 0 to that maximum value, there exists a current in the first coil, or momentary deflection is seen. When that field lines become constant, then the deflection becomes zero. When you switch the key off, then again from maximum field lines to zero, so there is a change in magnetic field lines, which again causes the momentary deflection, and then the deflection becomes zero. This is the basic concept of all the three experiments. There must be a change in magnetic field lines associated with the coil with which the galvanometer is connected. Then and then the electric current is produced or induced, we can say, and that number of field lines associated with the coil is the new concept, that is the concept of the magnetic flux, which is discussed in the next topic. Magnetic flux through the plane area A placed in a uniform magnetic field B is given by phi B, that is magnetic flux, okay, that is defined as B dot A. Both are vectors, B and A, so it is BA cos theta. Okay, so whenever area, or we can say this plane, is kept in the magnetic field, say magnetic field is in this direction, okay, and the area vector is always perpendicular to the surface, let the angle between B and A is theta, okay, then magnetic flux, that is giving you the idea about the field lines, okay, that is defined as B dot A or BA cos theta. Okay, theta is the angle between vector B and vector A. Okay, if the magnetic field has different magnitudes and direction, okay, say for example you have a curved surface and you have different value of magnetic field at different places, okay, somewhere here the magnetic field is B1, somewhere here the magnetic field is B2, okay, then what will you do? You will just take those small area elements and find individual flux. The total flux can be found by summing all the flux which you are passing for different small area, okay. So for the first area, say for example flux is B1 dA1, where B1 is the magnetic field at this first segment. This is a second segment where magnetic field is B2, area element is dA2, and so on. And if you take the summation over entire surface, then you will get the total flux here, sigma all, which represent all the small area elements on which you are taking the summation Bi dAi. It's very easy to understand, where all stands for summation over all the area elements dAi, that is dA1, dA2 up to dAn, comprising the surfaces, and Bi is the magnetic field at different area elements. Okay. The SI unit is Weber or Tesla meter square. Okay. Now magnetic flux is a scalar quantity that you can understand. It is a scalar product, B dot A dot product. Okay. Now we move further. That is, Faraday has some of the different experiments, and he stated from different experiment he observed. Okay. Faraday stated experimental observations in the form of a law which is called the Faraday's law of electromagnetic induction. The law is stated like this: the magnitude of the induced electromotive force. Now we talk about magnitude, value. Magnitude of induced electromotive force in a circuit is equal to the time rate of change of magnetic flux through the circuit. So it is rate of change of flux which gives you the magnitude of electromotive force. Mathematically it can be written as E, that is electromotive force, is equal to d phi b by dt. Phi b is the magnetic flux, so rate of change of magnetic flux gives you the electromotive force. Here negative sign has come. That negative sign is because of Lenz's law that is discussed in the next topic. Okay. Negative sign shows the Lenz's law. Now, if you have n number of turns, say for example you have one turn and you have joined the galvanometer with this coil. Okay, with this coil you have joined the galvanometer. Okay, and like this it is, and magnet is brought close to the coil. Okay, then galvanometer shows the deflection. If you have n turns, instead of 1 you have say 10 turns, 15 turns, 1000 turns. Okay, then this electromotive force will become n times the rate of change of magnetic flux, or we can say EMF E is equal to minus n d phi b by dt. Okay. The induced EMF can be increased by increasing the number of turns of a closed coil. The flux can be changed by changing any one or more of terms B, A or theta. Either you change the value of magnetic field, the flux changes. If you change A, then also flux changes. If you change theta, angle between B and A, then also the flux changes. You can change the flux by changing either of these one or all simultaneously. Okay, that can be seen from different experiments. Okay, the flux can also be altered by changing the shape of the coil. If you have a coil, say for example you have a circular coil, instead of make it triangle, automatically circle માંથી triangle બની જાય, square બની જાય, એવી કોઈ ગોઠવણ હોય, then also the magnetic flux associated with it changes. Okay, or you can just rotate the coil in the magnetic field. Okay, so theta between magnetic field and area vector changes, then also flux changes and electromotive force can be produced. Okay, now Lenz's law and conservation of energy. Okay, now that we shall discuss in the second video. Okay, thank you very much.